Take number 47. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5.
Our brewers are the best, materials the best, the equipment is the best, for we test, so it outsells, because it excels. Duquesne, have a Duke, Duquesne, have a Duke, the prince of Pilsner's Duquesne, premium Duquesne, it outsells, because it excels.
Okay, today we will be doing something slightly different. I'm going to record this little intro and, stick with the brand and all that sort of thing. We're going to move on and talk about phase spaces, and in order to do that, we're going to go back to the predator-prey model that we had early in the semester. We're going to fade over to the computer monitor here in just a little bit, and I'm going to walk through some more details on the predator-prey model on the computer. Your midterms are being graded slowly. Almost done. I will make a little video about those when they're ready, hopefully tomorrow. All right, so I'm going to go over to the computer and we'll pick up with a screen capture from the computer.
There's a tingle in the taste of Fitker's beer.
There's a tingle in the taste of Fitker's beer.
Have a flavor fling, let your taste buds sing to the tingle in the taste of Fitker's beer. Flavor of the great North Shore.
Right, so here we are at the screen. This is our familiar, hopefully familiar, maybe not well remembered, but this is basically the model we looked at way back in week number 4, I think it was, that shows a model that has a predator, lynx in this case, and a prey, rabbits, and those two, the populations of those two are related to each other. The lynx increase is related to the number of rabbits. Its decrease is related to its lifespan. Rabbits increase based on rabbit fecundity, and rabbits decline based on lynx predation. And that's the basic model. As you'll recall, I did not, well, maybe you don't recall, I had trouble scaling this. But a guy called Tom Fitteman did a nice version of this, and that's the model that we're going to use. So he has generalized it. The equations that describe this relationship are called the Lotka-Volterra predator-prey equations system. And here the predators are, well, we called them lynx, and I think I got the colors backwards. And then the prey are rabbits in the previous description. Here's the link that brings, relates the increase of lynx to the number of rabbits, and here's the link that relates the decline in rabbits to the number of predators. These elements here are the scaling things that Fitteman talks about here. But basically what they are, what this loop of things does is it says the rate of growth in the predators is related to the number of prey, and over here it says that the prey decrease is related to the number of predators. Now there's a lot of detail in here, and we're going to work our way through it. So let's see. So it's basically the same model. These things in green are variables that have been introduced to allow the scaling, to make things nice and clean. These fractional rates I've already talked about. The predator growth per prey, where is that? Predator growth per prey. Delta is the name of the variable in the formal equations. That's here. This is the fractional predator growth. This is we would have called this FB in our modeling. And then for the predators, and FD is essentially a lifetime for the predators. And then this is exactly how we would have done things before for the prey. That is, there's a certain number of prey, and there's a rate at which they grow, and that determines the growth rate. And then the decrease rate is how many rabbits there are and how quickly they're being eaten. Over here, in this graph here, is the time series of the predators and the prey. The predators are in blue, and the prey are in green. So these are lynx, and these are rabbits in our terminology. You can see that there are always, not always, but at the peak of rabbits is higher than that for the predators, and that in this arbitrary time there are roughly three cycles. There's roughly three cycles. Apologies about the colors. We're going to do some mucking around with variables over here, and there'll be the original base case, which is what we have here, will show up as these little lines. Now, this is the panel, the part that is new. And in this graph, it is a graph, it is, depending on the voice you want to use, plotted along this axis the number of prey, and along this axis the number of predators. And again, so note that this is 200 and this is 400. So I'm expecting that there may be many more prey than there are predators as we go through some of our exercises going ahead. Each, you can't see this, but this is plotted as dots. Each dot here represents one instant in time. So if we start, let's say at time 20, the number of prey is very low. It's somewhere back in here, and while the number of predators is slightly higher. So that would give us a dot. Let's say this is, let's take this one because it's easy, 75 and 75. So at 75 is going to be about here on this plot. So at this point in time, we would get one dot here. And you can see that as time progresses, let's see, the predators are declining, and as we go this way, the predators are declining and the prey are declining. So we would move this direction around here. At this point, the prey are at their maximum. So that would be one of these here, or here. While the predators are still increasing. Similarly, with the prey at their maximum predator happens back in here at a time when prey are somewhat low. So this diagram here, each of these dots is an allowable state of this system. And the state, I started talking about that a while ago, but the idea of state is that the number, the state of a system is described by the values of parameters at any given time. And in this case, our parameters are the stock of predators and the stock of prey. These dots represent the only possible states for this system when the parameters are set at their default values for this model. So we can't have, with the parameters as they are set here, we will never have a time when there are 320 rabbits and 50 lynx. It just won't happen. And there won't be times inside here either. These are the only states that the system will be in, and it's an equilibrium system. You can see that it goes that these things essentially go around in a circle. This sort of egg-shaped diagram. Did I complain about the colors yet? I don't have control over the colors, so you have to. Keeping track of what's going on can be a little bit difficult. Let's see. So let's muck around here with this model a little bit. And this is the VenSim software. It's been pretty stable, so hopefully it won't crash. It's PC software that's been ported to the Mac, and it seems to work reasonably well. All right, so we've now entered into a simulation mode in the model. That's what all these little graphs are graphs of, and this one's the fractional predation rate. And actually, before we do that, let's stop this and look at what some of these are. So this is the predator growth parameter. So this parameter here controls how fast the predators grow as a function of the number of prey. And then there's these other scaling elements. And so this combines with these things to give us the what we would call the fractional birth rate for the predators based on the number of prey. Similarly, this parameter here tells us what the how fast the predators are eating bunnies. Sorry, and these here do the same kinds of scaling. This relative initial prey and relative initial predators set the that's not true. Reference predators and reference prey set the starting point for these for any given run of this model. And we'll muck around with these later on. But for right now, let's just note that there are 10 predators to start, 10 lynx, and 100 rabbits when we start. All right, this is getting a bit long in the tooth. Maybe it's time for a break.
Let's all go to the lobby. Let's all go to the lobby. Let's all go to the lobby to get ourselves a treat.
Delicious things to eat.
The popcorn can't be beat.